Welcome back to Getting It Done, tutorials for solving physics problems. So if you looked at one of the previous tutorials, I was showing you how to reduce a circuit for capacitors. So I thought, let's put on the board a little bit more of an advanced problem, because one of the things that you're going to have to do is recognize when you're looking at a series and parallel circuit. So I thought I'd throw one on here that might be a little challenging so it can help get you practice on what to look for. So if you look up here, we have a power supply with some voltage. Again, we're just going to keep it theoretical, meaning we'll just label the capacitance. We're not going to give them values. You can make up your own values and then do the problem yourself. What I want to do is just break down what's in series and what's in parallel. So when we look at this problem, what's the first thing do you think you can see that you can reduce? I'll give you a second to think. Okay, what did you see? Did you think that maybe C3 was in parallel with C5? If you did, you'd be wrong. Let me explain why. See, on the right side of C5 and C3, they are in common at this junction. But here's the problem. They're not in common on the right side. Why? Because C6 is in the way. So you have to recognize that to have two elements in common, you can't have anything in between the connection on that side of the element. So you might ask, well, okay, is C3 and C4 in parallel? No, they're not. Why? Because though they are both in common on the right side at this junction, C2 is in the way between their junction on the junction on the left side of C3 and C4. Therefore, C3 and C4 are not in parallel. Well, if they're not in parallel, are they in series? Well, let's check. If the current goes through C3, it doesn't have to go through 4. It could go up through 6. So now we know they're not in series. If the current goes through 5, it doesn't have to go through 3C. It doesn't have to go through C2. But wait a minute. It does have to go through C6. So C6 and C5 are in series. So that's probably, in fact, in this particular problem, that's the only thing that we can reduce. So let's go ahead and do that. There's one other thing I want to wanted to mention. The one thing about circuit diagrams is circuit diagrams are geometry independent. It doesn't really matter where you put a capacitor when you redraw the circuit. Let me just give you a quick example. If I started off with two capacitors in series, like this. Here's the power supply, and I reduce this circuit. When I redraw it, I could redraw it where the capacitor is up here. I could also draw the circuit where the capacitor is on the side. It doesn't matter. As long as the connections are in common, then it doesn't matter where you place the capacitor. So remember that, because sometimes you're looking at the right place to put it. The right place to put it is as long as the connections are proper, not whether it's on the side or on the top. So let's get to our circuit reduction. Since I know that I can reduce C5 and C6 in parallel, here we go. We'll redraw the circuit with these two combined. So this, again, can be a little tedious, but it's not hard. And that's what's important. So now I'll redraw the circuit. Here's our capacitor here. This is C2. Here's our diagonal capacitor. That's C3. And we had that one down here. That's C4. But now I can take this capacitor and put it here. And that is now C7. I've added C5 and C3 together, so that makes C7. Now, how did I add them? I added them in series. Therefore, 1 over C7 is equal to 1 over C5 plus 1 over C6. Put your numbers in after we get all of our equations together. Now I look at our circuit. What's in parallel? Well, it turns out that C3 is in parallel with C7. Why? Because the top part of C7 is in common with the left side of C3 via this junction. And the bottom part of C7 is in common with the right side of C3 at this junction. So they're in common. And by the way, this circuit would be just as valid as if I drew it like this. This could be C7, and this could be C3. And this one over here was C2, and down here, this is C4. So this circuit and this circuit, whoops, these two circuits, though they look different, are exactly the same circuit. Remember, the circuit diagrams are geometry independent. But let's go ahead and reduce this. So if we add these two in parallel, that gives us our new circuit. We redraw this. I know, boy, I hate redrawing this. There's a way to avoid it, but I'll be honest with you, that method, I think, gets really messy and really complicated, so I tend not to teach it. All right, so then we have this circuit, and here's our C4 down here. And this is now C8. How did we get C8? We got C8 by adding C3 and C7 in parallel. Therefore, C8 is equal to what was that? C3 plus C7. Now we have C8. Okay, now what do we have? Can you tell? You tell me. If you said that you have C8 and C4 in series, you would be right. So now we can reduce that circuit and say, by the way, I keep forgetting to put my voltage by my power supply, but we can go ahead and rewrite this as C1, C3, and we can combine C8 and C4. Oh, by the way, when we combine them, that becomes C9. Here's our power supply. So now, once we combine C4 and C8, you have C9 in parallel with C3. So then we can reduce that, and since they're in parallel, that would become C10. So C10 is equal to C9 plus C3. If we combine those two, I'll just do it over here. Now we get C1 combined with, this would be C10. Here's our power supply. Put our little voltage there. Okay, so now we have C1 and C10 in series. So that equivalent capacitance will be C11. So C11, 1 over C11, will be equal to 1 over C1 plus 1 over C10. Remembering that those are actually values once you plug in your number. So our final circuit, our equivalent capacitance, which is C11, is right here. So if your problem was what's the equivalent capacitance of the circuit, you're ready to stop here, plug in your numbers, get your value. We'll come back in the next part of the tutorial, and we'll look at finding out what the equivalent charge is and working backwards to find the charge on each of the capacitors. Hi, Kent again. I just wanted to remind you to like and subscribe. It'll really help the show out. I made these tutorials to help people who are struggling in physics and solving problems by looking at the fundamentals that would make things a lot easier for you. So you can do something for me by hitting that like and subscribe button, and please leave a comment. Maybe you have a problem that I haven't addressed that you'd like me to address for you. Like and subscribe, and I'll try to get right on that. Thanks again.